In this video, we're going to talk about adjacency lists, adjacency matrices, and isomorphism. The idea behind adjacency is we consider two vertices adjacent if they are incident or if they share the same edge. Okay? So what we would do is label our vertices, A, B, C, D, whatever notation you want to choose. The representation and labeling is not unique. And then if we want to make an adjacency list, what we're going to do is we're going to list each vertex, and then we're going to list what we're adjacent to. So A is adjacent to the vertices B, C, and D. B is adjacent to A, C, and D. C is adjacent to just A and B, and D is adjacent to just A and B. Okay. An adjacency list gives a representation of the graph, not by listing explicitly the edges, but by listing all of the vertices that each vertex is adjacent to. Now over here I could do a similar thing. I could come up with an adjacency list. Now eventually what we're heading towards in this section is the idea of isomorphism. So before we move on to this next example, let's sort of think about some of the roots of this word. Iso means same and morph means shape. Eventually we're going to ask ourselves, are these two graphs really rearrangements of the same connections? Have we just sort of manipulated these edges and moved these vertices around? But we're not breaking any connections. Okay? So we could arbitrarily just go ahead and call these vertices A, B, C, and D, and we can come up with an adjacency list over here for this second graph. Okay, what's adjacent to A will be and D. Okay, now right now you might be looking at this and saying, well, these two can't be the same graph because over here A is adjacent to B, C, and D, and over here A is adjacent to B and D. Well, the choice we made for A here was kind of arbitrary, and if we wanted to have any chance of the vertex A over here matching the vertex A over here, we shouldn't have started at a vertex that only has a degree 2. So first we'll just do an adjacency list. It becomes a little bit of a difficult problem, and it's a difficult problem for computers because in order to show your isomorphic, you would actually have to show that there's some mapping. Just finish this up here. This would be the adjacency list if we chose this mapping. But there's no reason to think that this is the only way we can map these. And if we go back to our counting techniques, if we had 4 vertices, we could have 4 choices for A, 3 choices for B, 2 choices for C, and 1 choice for D, or 4 factorial different ways we could have labeled this graph. So that would be 24 possible checks for isomorphism before we determined whether or not any of them actually match this. Okay. Now since we're doing this by pen and paper, we can be a little bit more clever and strategic in how we label our graphs. So we know that this is not going to work. Right, let's try a different labeling that has a chance of working, and you might be able to sort of see visually how you could manipulate this graph without breaking any edges into this graph here. If we're going to have any chance at all, we better make the 2 over here that have degree 3, right? And sometimes it helps to kind of just go through that quick degree calculation, right? C and D have degree 2, so we better call this one maybe C. And that's arbitrary. I could have called this one C. Now once I pick C here, C in this case happens to be connected to A and B. So I have to make one of these A and one of these B. That means the other one has to be D. Now there's a lot of symmetry in both of these graphs, so we can sort of not lose too much sleep over this decision between A and B. But based on the complexity of the graph, right, if A was not connected to D and this one was, you'd have to make that decision over here. So as you go through checks for isomorphism, there's a difference between saying this is not an isomorphism versus is there any isomorphism. So you have to be a little bit careful that you run through all the possibilities or show that none of them is going to work. Now in this case, A is adjacent to B, C, and D. B is adjacent to A, C, and D. C is adjacent to A and B, and D is adjacent to A and B. And now you can see these have the same adjacency list, so we could say that these two graphs are in fact isomorphic, right? If we label this one over here G1 and this one G2, we can say that G1 and G2 are isomorphic. The word isomorphic can only really refer to a pair of graphs. You can't say a single graph is isomorphic. You can say a pair of graphs is isomorphic. Okay. Now another way to represent adjacency is through an adjacency matrix, and there are some things you can do with adjacency matrices, like count paths, that have some applications, and adjacency matrices are sometimes easier to model in programming. Because a matrix is really just a two-dimensional array. So if we're going to look at the adjacency matrix, what we would do is we would think about the rows as A, B, C, and D, and the columns as A, B, C, and D. And a matrix is really just a two-dimensional grid. In this case, we would do a 4x4 matrix. And we're going to put a 0 to represent no connection and a 1 to represent a connection. So when we look at A is not connected to A, but A is connected to B, C, and D. B is connected to A, not to itself. B is connected to C, and B is connected to D. C is not connected. C is connected to A and B, but not itself or D. And then D is connected to A and B, not itself or C. Okay, so this is our adjacency matrix over here, and if we did a similar adjacency matrix over here, we'd be able to show that they are the same. A is connected not to itself but B, C, and D. B is connected to A, C, and D but not itself. C is connected to only A and B, not itself or D. D is connected to A or B but not itself or D. Okay. Now you can see there's some symmetry to this matrix, right? Because if A is connected to D, then D has to be connected to A. So you're always going to have this sort of diagonal symmetry with these adjacency matrices. Okay? So if you want to show two graphs are isomorphic, you have to show that you can label them in such a way that either the adjacency lists or adjacency matrices are the same. Now the problem is, just because the adjacency matrices are different or the adjacency lists are different doesn't mean they're not isomorphic. It just means that the choice you made didn't work. Okay? Now, for these examples, it's going to be a little bit easier to show that these two are not isomorphic. Okay? The easiest ways to show you're not isomorphic are to show that you don't have the right number. You don't even have a chance. Okay? So over here, how many edges are there? How many vertices? Sorry, we'll start with vertices. The size of the set of vertices over here is 4. The size of the set of vertices is over 5. Over here is 5. Since, we'll call this again G1 just for name reference, and G2. Since G1 and G2 don't have the same number of vertices, they can't be isomorphic. So one of the easiest ways to rule out isomorphism is if you have graphs with a different number of vertices, if you decide to label these A, B, C, and D, no matter what you choose for A, B, C, and D here, you still got this other vertex that has nowhere in the original graph to map to, therefore they can't be the same. Okay? It's not often that you're going to come across this, but these are sort of the easy cases to rule out. Now in a case like this, we do have 5 vertices here, and we do have 5 vertices over here. So now we have to go through edges. Okay, now the way you count edges in a small graph like this, you can just do sort of tick marks. 1, 2, 3, 4, 5, 6, right? And the number of edges here is 6, and you can go 1, 2, 3, 4, 5, 6, and you could say here the number of edges is 6. Okay, so we have the right number of vertices and the right number of edges. We at least have a chance. Now the other way to count edges is to add up the degrees. And if we start labeling the degrees, we'll start to see a problem right away over here. This vertex on the end here, we haven't given it a label yet, but we could, has a degree of 1. Okay? If these two graphs are going to be isomorphic, there must be a vertex over here to map it to. But if we go through here, we've got a degree of 2, degree of 2, degree of 3, degree of 2, degree of 3. There's no vertex in this other graph to map it to. So in a case like this, we could say that G1 has a vertex with degree 1, but G2 has no such vertex to map it to. Therefore, G1 and G2 are not isomorphic. Okay? So the easiest way to rule out isomorphism is to show you have not even a chance with the different number of vertices and edges. But you could have not a degree match, right? Over here you can see you have a 3, 3, 2, and 3, and here you have 2 2s, 3 2s actually, and 2 3s. It's possible, although it's a little bit hard to come up with examples, that you could have all the same number of degrees on both graphs, but the way they're connected is different, and that's where it becomes sort of the hardest to figure out. So it's a little bit more challenging than it looks. On a small graph like this, it's pretty easy to find the isomorphism. In fact, sometimes people have good spatial relations. You can sort of imagine untwisting some of these vertices or moving them over and keeping the edges together, and you could probably see exactly how one would fold into the other or turn into the other. But as graphs get big and we want to represent them, on a computer and thinking about an algorithm to show isomorphism, it becomes a pretty big problem. Okay, and it's one of these intractable problems that for a generic size, the computational time to run through all possible isomorphism mappings for testing for isomorphism is intractable. All right, so try some examples. Make sure you understand what it takes to show when two things are isomorphic. Make sure you understand all the different ways you could not be isomorphic. Okay. But remember, just saying that the two adjacency matrices aren't the same is not enough for not isomorphism. Okay, so give it a practice to see how you do.